recording on this computer. Let me share my screen. All right, so this week we are here. We're gonna go over numerical approach. So what I did is, your book is explained like, you don't see anything. Why? No, get my cable. All right. So your book, the author of the book explained through 2 videos the Newton-Raphson method. All right. So instead of repeating him, I posted the videos here. They're 2 short videos, like 6 minutes each. If you're interested in numerical method, if you're a graduate student, if you're using robotics like for hands-on actual projects in simulation, I suggest you go over this. This is basically the method you want to find roots, you know, a function. You guess and then try to see how close you get. You've used this probably before. This has Jacobian, right? And you know what Jacobian is. What I'll do is I'll talk more like higher level. So Newton-Raphson is one of the methods. So I'll introduce the 2 methods, and then you should be fine anytime reading any literature. All right. So I'm originally, this was in the previous lecture, but I moved it here, trying to organize things. I posted the solution to CP 14, 15, 16. I'm going to go over CP 16 right now, and then I'll start the lecture. Okay. Also, homework 3 is posted, so start working on it. Don't leave anything for last minute. I mean, you can, but I suggest not to. Has anybody been watching the videos, the recording? How's the quality of the sound now? Is it better or is it still the same as before? I'm trying to stay close to the computer, but it's difficult. All right, so for CP16, so this is from your book. So if you start inverse kinematic section, as soon as you open the chapter, you'll see the 2R. And if you remember, this was the motivation when you started inverse kinematic. So you already had the solution of a lefty and righty, if you remember. So how to get that? When you draw the configuration, you will see that this is basically what I did in the example right before you start this class participation. So you see that even the 2 robots are different. The other robot from the top view look like this one, right? So depending on the configuration, when you look at the appropriate plane, you might end up with the same robot, and everything else is the same. So here, the thing that I added, so most of you, when I look, you did a good job. So you had theta 1, some angle, let's say gamma minus alpha, and then theta 2 is 180 or pi minus beta, right? So this question has 3 solutions, right? One solution, if L1, L2, one solution is that your X and Y is outside of workspace. So one solution is there's no solution, right? And that was the second question I asked you, what's the workspace, like how far you can reach, right? So one solution is there's no solution exists. Then there is 2 solutions, righty or elbow down, and lefty or elbow up. So if you remember, you can reach, if this is your robot, you can reach this point X and Y through here or through here. Same length, right? So the purple one is elbow up. The pink one is elbow up. The purple one or the bottom one is elbow down. So you can reach the same configuration, use 2 different configurations to reach the same points, right? So this can have 1, 2, 3. What is the case that you will have 1 solution? Let's say if your robot has to, let's go here, extend to reach that X and Y point. There's only 1 solution, right? You only have 1 theta, because the other solution laps in the same one. Or if your robot is like folded back on the second arm is folded back on the first arm, right? So these are the scenarios that you have 1 solution. So bringing this example so many times because your PA3 is going to be this robot to our planner. And I want you to think about the trajectory of the end effector, right? What happens? So you can use that knowledge when you're coding, when you're trying to approach your assignment next week, you know how this robot moves, right? Now, the question at the end was about the reach, like at what point the robot cannot reach. So if you think about this like a donut, right? So the outer shell is L1 plus L2. That's the max that the robot can reach. And the minimum is L1 minus L2. Let's assume L1 is greater than L2, right? You cannot reach further in terms of X and Y. You will be still moving around the circle, right? But the distance is not going to be closer. So it really depends on the length. So that was the question. So the reach of the robot is important to know in advance. So you have to think about it. What if I'm following a trajectory and it falls beyond my reach? What the robot has to do? It can't just freeze. There must be, so you can say that, hey, maybe go to the closest point. So it just travels to the closest point to create a smooth trajectory. Does that make sense? So these are the kind of thinking, or let's say problem solving methods I want you to have in mind when you see the program assignment next week, or any robotic problem when you're solving. If you're designing, one of your job probably will be trajectory tracking. So you need to know what's the workspace. So if you're designing a robot, you need to know where the workspace, required workspace is, then you design your robot based on that. Define the degree of freedom, and then how much, what servo kind of motor you have to buy that reaches that area. Basically, what is the thetas of your robot? Make sense? All right. So let's go to inverse kinematic blank numerical. All right. So in inverse kinematic problems, we said that we will usually get a position and orientation of our end effector. Let's call that x desired, right? So this x is not just the position. It could be x, y, z, and then theta, phi, psi. If it's planar, it's probably just x and y. All you care is about the position. Maybe you're just tracking the position. So first you need to know what the problem is, what you're trying to track. So when I say track, following to figure out, because we are solving for the position of our end effector, right? So we can say that you're tracking the solution. So let's say that x of d is a vector of Cartesian coordinates. Now we know that the forward kinematic for n link. So if it's planar, n link is n joined also, right? Then we can define a function. Let's say we have a forward kinematic function. We use DH table or POE method, and we have our forward kinematic, right? If we set a function g, this function of q, to be equal to x of desired minus forward kinematic at those set q values. So you have a desired place to be. You have forward kinematic that you can give joint values to reach to your desired, right? So think of it as a control problem. If the forward kinematic has the correct joint values, the forward kinematic expression will be equal to your desired position, right? So the difference will be 0. So think of it as control problem. If there is a difference, you want to drive it to 0, right? So we're trying to control the position of our robot from initial position. There's a forward kinematic. We give some random joint value, see where we end up, and then we find this difference. Our goal is to drive this to 0 to reach to our x of desire, correct? So that's the inverse kinematic problem. You're not going to find, okay, I'm going to guess 1 point and it's exactly going to be my x of desire. So especially with numerical method, you're using an iterative, like, hey, let's just start from initial guess and then see how far I can get close to my x of desire. Again, x of desired is the state of the robot, x, y, z, and the orientation. Now, let's see, q, d is q desired, like desired joint variables. X desired is desired and effector position orientation. Okay, plus orientation. Now, if you wanted just to focus on position, there are 3 X, Y, Z. If you want all 6 of them, then N is 6. So you have vector 6 by 1, right? Now, there are 2 common methods to use. One is using inverse Jacobian, which Newton-Raphson is based on that. And you saw the videos that I posted, right? So that's just one method, using the inverse Jacobian. The other method is using Jacobian transpose, and then use gradient descent search algorithm to find the solution. Now, off of top of your head, which one of these 2 you think could be a little bit problematic? Which one? Yeah, so why? Yes. So both of these are numerical, right? These days with computers doing all the cool things they do and with the processor, we don't have problem with the processing or how fast the algorithm is, right? The problem is inverse Jacobian. So we have to make sure our Jacobian is invertible, right? So we have to, if it is square, then you have to find all the singularities. So make sure that it doesn't fall into singularity. Then if it is not a square, how are we gonna invert it, right? So it has to, you have to do something. So that might be faster, but you have to deal with that extra work, right? The other one, you're just using transpose Jacobian, but then using gradient search algorithm, which is like basically 1 or 2 line of like theory, and then the code part of it is also pretty straightforward. You can just go online, find the algorithm, and use it. All right. So your book is only explaining this method. Okay, I'm going to go over both of them. Now, Jacobian inverse, assuming that you have X of D desired, right, for a desired configuration, we will write the forward kinematic F of Q, and then we will use Taylor expansion because we have X is J Q dot, right? So we're kind of eliminating that Q dot, just expanding it. So using Taylor expansion, we're going to write it as F of Q would be FQ desired plus J Q desired. So Jacobian at desired value, Q minus Q desired. So you see that this is the error term, right? Plus some high order term. Now, if we neglect that high order term, we can write Q desired minus Q would be Jacobian inverse of your Q times X desired minus the forward kinematic. So wherever you see Q, it means that we join variable at that instant time. The desired value are the values that takes the end effector to the position that you want. So you usually for inverse kinematic, you will receive the X of desired, right? And your job is to deliver Q desired. Now, if this term is 0, if Q desired minus Q is 0, then Q is Q desired, right? So the goal is to drive this to 0. Make sense? Or to a value, a threshold that you're happy, because you might not be able, your algorithm might not converge because of the configuration of the robot. You'll have to define a threshold or vicinity that you'll be happy with, and then you call it good for convergence, right? Because we are using numerical method. The other 2 methods didn't work. The geometrical and analytical method didn't work. We couldn't find a good closed form solution, so we are using numerical. Michael? Now, assuming that the Jacobian is a square, and is invertible, now to find a solution, we can start with a guess, right? And then we're gonna find all the Q's So starting from guess and developing Q's, right? So Q, which is theta 1, theta 2, theta 3. Now, what do I do with this information? Michael. So I start from initial value, I guess some initial theta values, right? So what do I do? What do I do from here? So think about, you want to drive this to a desired position, right? You have initial theta values. How can I relate these initial theta values to something that's comparable to desired position? Adnan.
So you use theory or be able to calculate the like theoretical.
Use your forward kinematic expression, plug in all these initial theta values you guess into that, so you get the position and orientation, right? And then you compare what you have with the desired, and you see if there's a difference. So now it becomes a control problem. Now you have to drive this difference to 0. So there should be now a different guess. We can usually use some steps, right? You can define a constant value for it. You can define it based on to be a function of k, like, you know, or it could be a matrix that you use a diagonal, like weight. You say that, if you're into a robot, maybe the theta 1 is more important, has more weight, because whenever theta 1 moves, it moves the end effector, because it moves both links. So theta 1 actually moves joint 2 too. So theta 1 should have more weight if you're thinking using the covariance matrix, right? The diagonal. So you can define some weight. So this joint has more effect of the position of my end effector. So I'm going to give it a number that will have more effect. And then once you recalculate, the new iteration has more basically calculated based on the importance of your first joint. That is also one way of defining step. Or you can say, no, for time 0 to 10, go 0.1 step. And I'm going to solve and see if I converge or not.
So does this concept happen before the levels or as it's
so when you're doing this, you're trying to figure out, okay, so that's the problem. If this is real time, or you're going to define it before, right? So there are two approaches. If you want to do it real time, you probably already figured out a proper step size, and you're getting some input from environment, for example, camera. So keep checking how far you are. So you have realistic error, right? If you want to do it real time. If you're doing before, like simulation, you want to know what would be the optimized path, then you're doing it without the robot actually moving. You say, I need to get from point A to point B. I probably have 2 obstacles to go around. What's the best path to go, right? So there are 2 approaches. Whenever you're doing real time, the best way is to have another input from environment. So it can see if you are physically getting closer to your goal or not. All right, so now the algorithm itself, so QK, so this is K iteration, is going to be QK minus 1 iteration, previous iteration, plus alpha K, so this is your step, how far you're changing, times J inverse of QK minus 1. So calculate the Jacobian of your previous step, times X desired minus F forward kinematic of your previous step. So this gives you the amount of error, right, that you are from where you want to be. And remember, Jacobian was mapping of how to get from, like, how your joint values will affect your point position. So multiplying by that. So now step 0, your initial guess will be here, and your first, because this you can set to 0, all of them. Or you can say, I think it's like 30 degrees and 60. You plug in like theta 1, theta 2 for 30 and 60. You plug in here, calculate this value, and you see that my second is going to be that. And then you're checking against your actual desired position. And you have to check the convergence of your algorithm. If your convergence will continue until you reach the point. And then I talked about alpha K could be just, it could be used to adjust the convergence. Sometimes you need a really close convergence or exact, like if you are working in NASA, you really want to make sure that everything connects, right? But if it is, I don't know, on Earth, very slow system, and you're good when you are 1 centimeter from your goal, that would be your threshold. You can adjust that alpha K for that. Make sense? So this is basically that, so Newton-Raphson also follows the same thing. But there are other methods that use this concept. Now, what if our Jacobian is not a square? A lot of robots, like when is our Jacobian square for what kind of robot? What kind of manipulators? Let's say you are interested in finding position and orientation. So your robot has 3 position, 3 orientation, so 6 total. What configuration, what robot, like how many links or joint, how many joints you should have to create a square Jacobian? So what is the square matrix? Ben, what's the square matrix? Okay, so the dimension, right? Row equal to column. So if one of them is 6, which is the number of the variable that you're going to find your output, to have a square matrix, what should be the number of your input? Equal, right? 6, so 6 by 6. So only for, if you are trying to find all 6 position and orientation for a robot, only in case of 6 or joints, so the 6 joints, it could be R or D, could be either of them, right? That's the only case that we will get a square matrix, like Puma that we saw the other day, right? If you're trying to find track a position in a planner, so you're trying to track X and Y, what should be the number of joints in your robot to have a square matrix? So you're trying to find X and Y. So your output is X, Y, 2, right? So your Jacobian has to be 2 by 2. So you have to have 2 joints. Other than those cases, so if your robot has 3 joints, you're still in a plane or you're in space, then your Jacobian is either going to be fat or tall, right? Number of rows more than number column or the other way around. So for those, well, for our cases, we're only going to have fat Jacobians. But in general, if you have non-square matrix, if you want to fix it to a square matrix, you can use pseudo inverse. Now, for right pseudo inverse, you will get the transpose of your matrix multiplied by the matrix transpose inverse. For lefty, you will follow this. Now, for us, we always have, like, if we want to find all 6 position and orientation, so that number is fixed. Our joints could be less than that, right? So if you find that it will be the righty case, then KQ will change to QK minus 1, sorry, plus, so QK is the previous joint variable, AK, this will change to pseudo inverse. Everything else remains the same. Q desired, which is X desired, right? Minus FQ minus 1. Okay, minus 1. So the only thing that changed is instead of J inverse, you put the pseudo inverse. And this is how to do the pseudo inverse. So if you have non-square, you can fix it and then continue the same algorithm. Now the second one is you can use Jacobian transpose method. So this way, we are kind of solving an optimization problem. We're going to define a cost function, and then we are going to drive that cost to zero, right? Or to the value that you're interested in. So you define a cost function, 1/2 FQ minus X of desired transpose times FQ minus X desired, right? Again, now X desired is the desired configuration. Could be X and Y, X and Y and Z, or whatever from 1 to 6 item that you have. And then your FQ is your forward kinematic, the current position with all the Q, theta or D values. Once you have that, you're going to find the gradient of the cost function, and the gradient of cost function will be equal to J transpose Q FQ minus X of Q out. If you use the gradient descent, then you're going to have KQ would be KQ minus 1 previous step minus alpha K, this time gradient descent of your previous step, which we are going to plug in from here, QK minus 1, alpha K, J transpose, QK minus 1, F, QK minus 1, minus X of desired. Now, here alpha K is greater than 0, step size, same thing. You can define covariance, you can define a fixed step size, if you function of K. It's like really your choice how you like to define this for the convergence of your algorithm, right? Now, would we have any problem with the Jacobian here? No, you can just transpose it, right? It doesn't matter if it's a square or not. So these are two distinct methods, yes.
It's not the pseudo inverse Jacobian?
No, this is transpose.
Okay.
So you don't have pseudo inverse, this is transpose. That's why we don't have that problem here anymore. So we don't have to, otherwise you have to check your, so here's an example. I'm not gonna have the code again. I'm not expecting you to do that for this class, right? So that's why I didn't want to talk about it, but since you asked, I included it. It's also good if you want to continue, if you're reading literature, following your book, things will make a lot more sense. And if you're a grad student, I suggest grab a 2R link, the ARM, right? Write the code for it and see if you get solution that makes sense to you, because you can find the solution using your analytical or geometrical method and you can match, right? Now, let's talk about this example. Inverse kinematic solution using Jacobian inverse method for RR planner, so the ARM, right? Now, let's assume our desired end effector coordinate is X desired 0.2 and 1.13. I'm going to draw that. What does this mean? This means that if you have this plane, X and Y, right? Let's say here is 0, 0. We want to end up in a position that is, so if this was my 0, let's say 0.2 is here and 1.3, let's say is here. I want to get here, 0.2 and 1.3. We know the configuration of the robot is this, right? Would this be theta 1 and then theta 2, right? So we want to find what theta 1 and theta 2 will drive it there. So we need to find basically these two values. And so I'm going to say desired. You see that this will immediately tell you that, hey, I have another checkpoint. After I figured out theta 1, there will be a point for theta 2. It could always be lefty and righty also, correct? So you have two options basically when you find this. But now when you're using an algorithm, you're trying to figure out the convergence, you want to just go one way, right? Find one solution. You don't want to, let's say start from an example. Let's say our first guess is going to be something like that, because the length of the link are fixed, right? You're gonna start from initial guess. I'm gonna call this x0, y0. Let's say x0, y0 is here, which will translate into, so you start from theta 1, 0, and theta 2, 0, right? You say that, let's say my first theta is at 30 degrees, my second is at 45. Let's see where it ends up. You put in your forward kinematic, you'll get x0 and y0. You compare, you see that you're not there. Then you're gonna move. So your algorithm has to understand, it has to move this way, right? Decrease this. So when you get close, I'm gonna delete it, but I'm gonna draw it right now. So you kind of go here, get closer. But then when you're here, one of the solution could be this way, it's the same. You see that there's a jerk. Or at any point, if you're not checking if you're following lefty or righty solution, the motion will could look like this. Right? So if it was in reality, the robot will keep moving back and forth and moving in the space to get to the point. So you have to check for the solution that they are following, let's say the right side, the correct side of the solution. So if it's righty, always is righty. Does that make sense? Hopefully it does. So let's say we start from initial guess theta 1.25 radian, theta 2.75 radian, and then you choose a step size. Choose a step size, and then it will take some iteration from here to get there. So this, I use this example from a book. I don't have the code, but I give you all the data from it. The first method, the inverse Jacobian, found the solution after 10 iteration. The Jacobian transpose found it after 30 iteration. Now, at this age of computers, it really doesn't matter. They're as fast. You can get the time, right? But if for your application it matters how fast it goes, then you can do both and then find which one is more optimal. Then in real time, use that method, right? What will your result, like output, would look like is you're probably gonna have iteration, theta 1, theta 2, iteration 1. Like after your initial value, let's say you get negative 0.33 and then 2.67, you go iteration 2, you get, let's say 0.805, then 2.1. So every time you find this, you have to go find the position of end effector, right? And then you compare until you get to the value, which is 0.2 and 1.3, and then you'll stop. Let's say it's iteration 10, some values, and you could grab that. Or you get to a threshold that you're happy, you stop. Make sense? So that's basically numerical method. Cool. Any questions? Yes. Mm-hmm.
The values that you put into the equation you gave us before are vectors.
Here. The Q is 0.5650 and 1.0 in radians, 6 step. So your Q is your theta 1, theta 2, right? So do you remember, so since we are using the Jacobian, we had xy is equal to Jacobian times theta dot 1, theta dot 2. So this is Q desired. So let's say, so this is Q, your Q desired, but doesn't matter. So your Q initial, let's say Q0, is whatever value, 0.25 and 0.75, right? You start from here, and then for this Q, you put it in your forward kinematic, and then you get theta 1 and theta 2, x1 and y, x and y, let's say. X0, x. If this was step 0, you shall guess, next is step 1, right? So you get x and y first. Then you have to compare to see how far you're from the desired. If you're not far enough, if you're not happy with the distance, you have to go iteration 2. Now this x and y is your new current position, right? and you had your theta 1, theta 2. So you're changing your theta 1, theta 2 at time 0. You add by the step, let's say add half a degree each time. You add that, so that's your new theta 1, theta 2. You're plugging back again to the flow kinematic, find your new x and y, and then compare. This is the convergence. You're comparing for convergence. You go until you're happy. Sometimes you might not converge. There's no solution. Sometimes you might be, you didn't think about the reach, like if this is in the, like it's reachable, right? So your algorithm is trying to work and never finds anything. And since you don't have anything to execute out of, it just goes to forever run, right? So you have to think about first, it's reachable. Second, make sure that there's righty lefty. And then third, you just run the algorithm, and then you'll have a good threshold for convergence. It really depends on what you want to do. Like, let's say you can say check all the values because you're solving these locally, right? So let's say, especially when you're using gradient descent, you kind of are thinking about that. Let's say you're going around a point, you find solution, then you keep going up. You want to check your minimum value and see how far you are, and you've never reached to that. So this is you end up in local minimum. There are methods that, like, hey, if you're solving and then you just at your lowest point and you never reach, maybe you need to change and start your initial guess somewhere closer, so you're not trapped in the local minimum. So these are, if you have time later for trajectory planning, I'll discuss these and discuss gradient descent method for path planning. At this point, just know that this exists. That's a method. Hopefully, if you have time, you will go over all of that. Yeah.
Yeah, you said it's different. Like some sort of error.
Yeah. Yeah, because you're trying. So for the second method, you're using cost function, right? So that's the square root of, yeah. So there are different methods also to find like your error. You want to probably go with the square root. The square of it, not the error itself, because it can get larger faster. So you don't have to actually run as much. That's the point there. So to the inverse, when your Jacobian is not squared, then you have to find the pseudo inverse of that. Just make sure that it comes square. So you can find the inverse. Oh, yes. So first method, if you cannot find the inverse of the Jacobian, you can do anything. If you're like math, I will tell you that you can find it. Yeah. But the second method, it will not cause you trouble. So for the second method, you don't even find it in the inverse. You just find the transpose. All right. So you okay, this is start homework 3. This is nothing today because I changed the lesson, so you will have that on Friday. But we have a little time. I want you to think about let's say you have a manipulator robot. I'm going to just use the 2R because I can't use my arm. So this is 2R. There's one going here, one going here. Let's say this manipulator is manipulating something, and let's say it hits the wall or touching something, right? So like you have to push. So when it contacts with an object, or like let's say a wall doing something, there will be some force and moment generated at the manipulator, right? Like if it's touching the wall, it's going to be contact force, right? So think about so these force and moments, how do they show their effect on the robot? So if there's a force, there's gonna be a torque created on the joints, right? Now, why is this important? Your joints are made of DC motors or some sort of actuator, right? So you have to consider these forces on when you're speccing the motor, or when I think when you get to control, you're gonna have force control. So you're gonna think about the effect of these forces and moments on each joint. Now, these force and moments, they are related using the Jacobian. How cool is that? So since we are in Jacobian, I'm just gonna show it to you, but we're gonna get to it in control. So this is just because we have a little time. You don't have to do anything with it. It's probably not even my annotated version. Let's say if F is Fx, Fy, Fz for forces, and then Nx, Ny, and Z for moments, right? Then you can say, so now these force and moments are gonna create torque and force on the joint. So there's gonna be a torque resisting the motion, right? So if there was like a force here, this torque is related to that force by the transpose of the Jacobian. So if, for example, you had this force was 1 Newton down, so let's say was 1 Newton downward. If you wanted to create the vector, it would be the negative y direction, so 0, -1. If you wanted to find the torque, we will find the Jacobian at that Q's, say theta 1, theta 2, we know what they are, and theta 2. Then multiply by 0, -1, we will get the torque caused by those forces. So Jacobian shows up a lot. And because Jacobian is a mapping, right, between the joint, all joints, and the end effector. So you can relate the joint variable to the position of the end effector, or joint variable velocity, the velocity of end effector, or the other way around. Forces on the end effector are related to the transpose of the Jacobian on each joint. So you will find how much torque is applied because of the action that the robot is taking. Now, when you want to spec the motors, you have to calculate those, right? So there will be the force, the torque to move the arm, plus the torque that has to resist, plus some safety factors, right? That's how you spec. So I just wanted to like think about it, right? You know, some of you I know are doing some projects. So these are the things that you want to think about if you're designing a robot. Like, how do I use this course in real life? That's how. That's how you are going to. So you're going to use Jacobian in real life when you are trying to spec the motor. Or you can say, let's buy the most expensive, $500. But that's why it's not going to break. That's one way, you know. The other way is to actually do the calculation properly. So using the theory from this course, even this is introduction class, to something that could have effect in real life. Sounds good? All right. See you on Friday.